Yes. All right. And so this thing that we're going to do is of much importance. In fact, it's very important. And as a chemist, at least there are certain techniques that you should develop. And volumetric analysis is a very important technique that there is a need to understand it. There has been studies showing that teachers have difficulties in handling it. There has been studies indicating that teachers have conceptual difficulties in these things. So we hope that as we go through, we'll get better understanding of the whole thing. Okay, so it is Unit 3, volumetric analysis. And for this very session, we will be looking at some terminologies in volumetric analysis, choice of indicators, and standardization of solutions. So our objectives are to be able to distinguish between equivalence points and endpoints in a titration exercise, distinguish between titrants and analytes in volumetric analysis. These are terminologies. Then distinguish between standard solution and primary standard solution. And then select appropriate indicator for an acid-base titration. Okay, then our final objective is to standardize an acid or a base using volumetric analysis. Okay, so let's look at these terminologies and what they imply. So volumetric analysis largely is a quantitative method which involves accurate measurement of volumes of solutions to estimate quantity of solute particles in a solution. We are dealing with numbers. We are dealing with measurements of volumes. Then we have equivalence point, which is a point in the titration reaction at which an equivalent amount of the base and acid are neutralized. How do we explain this? Now, let's say that you have an equation or you have a reaction between let's pick a very common reaction like sodium hydroxide and hydrochloric acid. So when you write that equation and you balance it, the balanced equation is happening at the equivalence point. So at that point, there is equivalent amount of the base and acid neutralized. So that is the point, the actual point that we have the neutralization happening. So if you are doing titration, then you have to stop at the equivalence point. When you have achieved equivalence, that is all. You don't continue with the titration. However, that is happening chemically, and it becomes very hard to tell that you have reached that point, okay? Because that is happening chemically, and you cannot see it, okay? So a way that you can see is to rely on something called the endpoint. At least that one gives us something physical that is not chemical. It happens physically, so we can catch, we can know that at least there is an equivalence point. So what is an endpoint? is a point in the titration reaction at which the base has been completely neutralized by the acid. Now, one thing that makes it a bit easy is that at the end point, because we use these indicators, at the end point, there's a color change. Now, there's a difference between the end point and equivalence point. Okay, the ideal thing that we would have looked for is the equivalence point, which is difficult to do. So you may not get the exact equivalence point since that is happening chemically. So we use the endpoint at least to tell that we are closer to the equivalence point. So the endpoint, the point at which we stop our titration and we take our reading is such that we are either slightly past the equivalence point or we've not gotten there. And so we have those uh, negative endpoint, negative the equivalence point, and then we have the positive equivalence point. That is to say that we may not be able to determine the exact equivalence point relying on the endpoint, but at least it gives us something that is closer to the point that we are looking at. And even in a titration or in a color titration, a titration that we rely on color change, sometimes it's even hard to catch the very drop that causes the color change. Somebody may add a little more, somebody. So you would realize that we are only trying to get something closer to the true value, but it is hard getting the true value. Then, titration as a term is a process of estimating the concentration of a solution of a substance by reacting it with standard solution of another substance. So in this titration, we want to know the concentration of one solution. So we don't know its solution. How do we do that? We get another solution whose concentration is accurately known. Then from the known concentration, we'll try to look at the relation between these two solutions or these two compounds. Then through the known, we can get to the unknown. And so standard solution, like I've said already, is a solution of known concentration. If the concentration is not known, it's not a standard solution. And primary standard solutions are solutions which are usually prepared by weighing and dissolving certain solid reagents in water to obtain accurate concentration of solutions. Okay. Then the process of determining the accurate concentration of a solution by titrating it against a primary standard solution is what we term as standardization. We are trying to standardize a solution. We are trying to find the concentration of another, and we are doing that through titration. So the process is called standardization. And then now in the titration process, we've got two components. We have the titrant and the analyte. At least there is a component in the burette and there's a component in the conical flask. So one is the titrant, one is the analyte. The titrant is a solution whose concentration is known in the titration. So it is the one that we are going to use it to find the unknown. So the unknown is the analyte. Now let me ask this question. Usually, since it's a neutralization reaction, we are expecting a reaction between acid and a base. Which one do we put in the burette and which one do we put in the conical flask? Is it the acid that we put in the burette or the base that we put in the burette? Class? Hello? Yes, George. After that, Robert.
Thank you, sir. I
Mhm.
I learned we put the acid in the burette and then the base in the conical flask.
Okay, thank you for your contribution. Yes, Robert.
Okay, so normally the acid is in the burette and the base is in the conical flask, but sometimes it can change. We can put the base in the burette and the acid in the conical flask, depending on the type of titration you are under doing.
All right. Thank you for your contribution. Okay, so the point is that there is not any uh, definition that a base should always be in the conical flask or acid should always be in the burette. There is nothing like that. Okay. And so let's not um say that maybe a base should always be in the conical. It could be anyway. Okay. But the problem is that when you have a base in the burette, it causes beading. Okay, so um in a layman's word, we will say that it appears like scratching the surface of the burette and makes it dirty, and when it is in it for long, I mean, it makes it such that you are not the burette becomes like cloudy and a bit dirty, and it makes reading difficult. Okay, the right term is beading, causes beading. And so if you are doing titration and you happen to put your base in the burette, it is a standard practice that right after you empty and then you wash the burette. But the acid is not restricted to the burette. The base is not restricted to the conical flask. It could be any way. But the titrant is always the one whose concentration is known, and the analyte is the one whose concentration is unknown. Yes, George.
Thank you, sir.
Mhm.
Please, can I get this cleared? I learned a teacher told us that because the acid is more corrosive than the base, when you are pipetting, it is advisable that you pipette the base rather than the acid. Is it true that like that?
So if it has
That
got to do with acid being corrosive, we still have acid in the burette, and so we should still have that effect on the burette.
but he was saying that maybe mistakenly you might um start the base, or if you are pipetting the acid
No, no,
and
but you see,
mistakenly it.
as in no, there is never pipette with your mouth. If that's what you want to mean, never pipette with your mouth.
Okay,
So that you
okay,
suck
sir.
it. It is I don't know, but it is only in our part of the world that we don't take safety protocols serious. But it is never a good practice to put a pipette in your, even when you're going to eat your own hands. You wash your hands before you eat. right? So if you
Yes, sir.
wash your hand before you eat, why would you pick a pipette and then put in your mouth? And apart from the pipe, let's even assume that you are pipetting a clean water, maybe a mineral water. You just pick the pipette that is just lying down, and then it is into your mouth. There is a problem there. It can cause you problems. Now
Okay, sir.
talk of now having an acid in a pipette and then pipetting it. It is never a good practice. If you go to a school and they don't have equipment for pipetting, request for it. Let them provide. Okay, let them provide. Get the suction bulbs, get them. These things are not too expensive for schools to buy, considering the problems that they can cause if students are pipetting
Okay, sir.
the mouth. All right. Okay.
Okay, thank
So you are welcome. Then we have titer. The titer is the volume of the solution in the burette which has reacted with the other solution in the conical flask. Whatever solution that is in the burette, the volume of it that reacts with whatever that is in the conical flask, that is the titer. George, is it a new hand or an old hand? Okay. So that's the title. So we go to the lab, we do the whole titration just to get the titer. If you have the titer, you may decide not to go to the lab to do a titration. So we go there so that we can get the titer. Because as for the volume in the conical flask, that one we measure. Usually we are using the pipette to measure, so you know it. But how much volume of the burette that you're going to use, that one, it should come through the experiment. Then we have indicators. Mostly we are doing color titration, and so we need indicators to tell the endpoints. Not all the time that in titration you need indicators. You may have equipment for determining the endpoint, but at least at the SHS level, you need these indicators, which are weak organic acids or bases, which change color in acid or alkaline media, depending on the pH of the solution. So how do we choose an indicator? This is going to help us at least. There are a number of indicators: the methyl orange, the phenolphthalein, the methyl red, the bromocrysols, and all those. There are a number of them, but the most common ones that we usually come across are the methyl orange and phenolphthalein. An acid can be strong or weak. A base can be strong or weak. Now, if we are dealing with strong acid against strong base, then either of them will do. We can use any of those two indicators. So if you are doing like potassium hydroxide and maybe sulfuric acid, we can use any of them. But when you're doing strong acid against weak base, the end solution will be slightly acidic. And so we go for indicator that works best in acidic region, and that is methyl orange. If we are doing weak acid against strong base, we expect a result solution that is slightly basic. So we go for phenolphthalein that is good in basic region, and we have phenolphthalein. However, if we are doing between weak acid and weak base, then we've not got indicator for that. Let's now look at reading and recording your titration data. The exercise should be repeated 2 or 3 times, ensuring that at least 2 title values do not differ by more than plus or minus 0.15. It's not ideal to do just one titration and you have your title, because you are humans. We are humans, and there are errors. And so you may do the first one, you may do the second one, and you not have same values. You do a third one, and it's going to confirm one of the first two, or it might also even be different. So you can do as many, but the values that you decide on, that this is my title, they shouldn't differ by more plus or more than plus or minus 0.15. So for example, if you had one that is like 22.1, then we expect another one either 22.1, 22.2, or maybe something around 21.9. Those are consistent values. You can select 2 or 3 or more. Just ensure that they are consistent. But then, because sometimes you are dealing with time, you cannot do a lot of them. At least 3 should be okay. All values, and in WASI, if it is more than that, I think they deduct some points for that. And as the difference keeps widening, then you are losing a lot of marks. All values in the table should be recorded to 2 decimal places. If it is 20, it becomes 20.00. If it is 21.2, it becomes 21.20, 2 decimal places. If you refuse that, minus 2 marks or minus 2 points. The volume of the solution in the burette is the average title value. Then the volume of the solution in the pipette is the volume of the pipette used. So these pipettes, you check the volume of the pipette. So when you pipette to the mark on the pipette, that is the volume of the pipette used. Then ensure that there are no cancellations in the table. I think when you cancel a table, it's around, I think, minus 4 marks or so. We don't deepen in a table. If you make a mistake in the table, like say the value is actually 22.2, but you mistakenly wrote 22.1, and sometimes we try to change the 1 into 2, you will lose marks for that. And so make sure that everything is accurate and on point. If you are not too sure, you can find a place that is not relevant, do a rough work there, do a table there, record your values there. If there are cancellations, you do that before now you come and write your final table. So let's ensure when you go to the school and you are doing trials, just ensure that students do the right thing. If they are coming to show you their table and they have committed any of these errors, let them go back, redo it, and then come before they go and mess up in the WASI. No deepening, no cancellation of a table. The final work, examiners wouldn't want to see that there was a table and there was an error in it, and so the whole table was cancelled. They can do that somewhere. Then they'll have the final work in the booklet. So let's take note of that. Let's try and look at a question. Any questions, please? Yes, George.
Please, in case there is a mistake in the table, and as you are saying, it has to be done somewhere before transferring it, and in the process of transferring it or copying it from the rough space, it's still there is an error. What should the student do?
If if at a point you make an error, then the best thing for a student to do is to accept the deduction of the marks.
So he cannot cancel the whole table
The,
and do
the
it
point is
again.
that you cancel the whole table, you lose marks. You make a
Okay.
mistake in the table, you lose marks for that. So any of them will attract you penalties. So be
So
accurate.
the only
Make
thing
sure
is to be very careful.
that's it. If you are transferring, just be sure that you are doing the and I think with practice, good practice, students will be good at that. So when you go, you'll be doing some titrations even before final exams. Insist that they do the right thing. I remember
Okay.
there was a year that I was trying some with. They were doing the mistakes, even though it was time. I insisted that they go back, do it. A student could come like 3 times. He will come, there's an error, I'll let him go. Then eventually, they were all doing the right thing. And in the WASI, there were no issues like that. So they can do it. Yes, Evans.
Okay, thank you. Please, sometimes, or let me ask, is it appropriate that the student does the first experiment, second experiment, and then the third one, he
Mhm.
try not to do it again, but analyze the result, and then try to manipulate the third one?
Mm. Then the student is not being a good chemist. The student is not being a good chemist because you can even have a case where it is the third one that is actually going to give you the right value. So you have to do it. If you have done two and you think the two are very consistent and you want to use it, that is fine. But don't assume that the next one is going to give me this value. I know they do a lot. Sometimes teachers will give title values and students will conjure and then they will do something to match up. It's better not if it is a two you want to use, you just go ahead and use the two. Don't try to forge. It's a dishonesty, and I don't think it is a good practice. I hope that's all right.
Yes, sir.
Okay. So let's try and see. There's a question here. Standardization of a solution in volumetric analysis. D is a solution containing 2 grams of sodium hydroxide per 500 cubic centimeters of solution. E is a solution of dilute tetraoxosulfuric acid. So we look at the instructions. We have to put E into the burette and then D into the conical flask. And our indicator is metal orange. And then you tabulate your burette readings and find average volume of acid used. At least students should do this thing. They should score up to this point. It's a free marks, and they have to get it. Up to this point, they have to get everything. If they will struggle, they should struggle from the next questions. But up to this point, they should get everything. Then the next question is from your result. Calculate the concentration of the acid in mole per cubic decimeters and in gram per cubic decimeters. So let's see. The experiment is already done for us. So our duty is just to use the values. So this is how a standard table should look like. we should have our burette readings and its units. Your first titration, second titration, third titration. If you want to do more, fourth titration, fifth titration, we should have it like this. Now, under just after the burette reading, we should have final, because we subtract the smaller from the bigger. It's just like putting a negative here. So we cannot write initial before we write the final. If we write initial before final, it means we are getting negative values. And so we should always have final before initial and volume of E used. All right, so let's look at what happened. The first one, the burette, the content of the burette was topped up to 0, and that is why this one started with 0. Oh, that's why this one started with 0. Now here, what happened was that after the first titration, whoever that did the titration decided not to add some of the content or the acid for it to get to 0. Wherever it got to, he started from there. He continued from there. And so the final here now becomes the starting point, or becomes the initial. Becomes the initial here. However, after this titration, the person decided to take it back, added some to it to make it 0.00. And that's why we have these values in the table. So then if we are to fill this table, we just subtract this from this, but from that. So let's look at it. So when we do those subtractions, we have these values. So assuming you were the one, which values were you going to use, or which values would you use? Assuming you were the one, this should be third. If you were the one, which values would you use? Yeah, anyone on that? Yes, George.
Please, are you talking about the average titer, or how to
Yeah.
calculate the average titer?
Yeah, which values would you use in your average titer?
I will use all the three. That is the 24.5, 24.5, and then 24.40, and then divide it by 3.
Okay. Yes, Robert. Yeah, Robert, go on. Okay.
Okay, sir. The values here I can see 24.50. It's 2, so I'll use the 2 and divide it by 2.
Okay. All right. Thank you. It will be best if you go for 1 and 2. But then it's not also bad if you decide to add the third one, because the difference is not, we are talking of plus or minus 0.15, and the difference is just 0.1, so it is not harmful using, but it is best if you use those 2. All right, so this is our average volume of E used. Okay, then they said that we should perform some calculations. So let's see. First of all, we had a standard, we had a titrant, and the titrant, the concentration of the titrant was known. It was given to us, even though it wasn't given directly. But if we look at this, the concentration is in here. So indirectly, we've been given concentration. There's a mass concentration here. That is 2 grams per 500 cubic centimeters. It's concentration. So the concentration is known. But it is hard to use mass concentration. And so we decide to change to amount concentration. And there's a relation between the mass concentration and amount concentration. And that's why, so if there is any point to start from, we have to start from here. So we first convert this one into amount concentration. And that is why we have this thing here. So amount concentration equals mass over molar mass times volume, or amount concentration equals rho, that is mass concentration over molar mass. The rho is here. It's mass over volume. So rho is inside here. That gives us 0.1 mole per cubic decimeters. All right. How do we interpret this?
Hello, sir.
Yes.
Please, the volume. How did you get the 0.5 DMP?
Okay, so in the question, we are given a volume here. The volume is 500 cubic centimeters. We work in liters or decimeters. And so we have to change this one into cubic decimeters by dividing it by 1,000. So when you divide this by 1,000, it gives us, so we are moving backwards 3 times. 1, 2, 3. That becomes 0.5. Is that all right? Okay. If you don't want it like that, you can first convert this one into mass concentration. That's 2 grams divided by 0.5. And the answer you get, you fix it into a formula. C equals rho over capital M, which is the molar mass. That makes it a bit longer. And so we use this formula. And we have 0.1 mole per cubic decimeters. How do we interpret this? Now, we will interpret this as for 1,000 cubic centimeters, there are 0.1 moles of sodium hydroxide in it, in the 1,000. Okay. In other words, this is what it means. A chemist went to the lab and then he put 0.1 moles of sodium hydroxide into 1,000 cubic centimeters of maybe distilled water to form the solution. Friends, do we understand? Good. So that's what this means. All right. Now, the chemist, whoever that did the titration, didn't actually use the whole of the 1,000 cubic centimeters. He just fetched some. We will look at that. Now, let's say it is you. George goes to the lab. He wants to do a titration. And so he fetches 0.1 moles of sodium hydroxide and he puts it into 1,000 cubic centimeters of distilled water to form that solution. However, in the titration, George is not going to use the whole of the 1,000 cubic. In fact, it's not that whole 1,000 cubic centimeters that he will add an indicator to it and then start titrating. He will just fetch a portion of the 1,000. Okay, like 25. So if that's the case, then if George had 0.1 moles in the whole of the 1,000 and he only fetched 25, obviously we are not going to have the whole of the 0.1 in the 25 that he has fetched because he dissolved it, stirred it evenly. So any portion that you fetch will only have some of the sodium hydroxide, but not all of it. So if the whole of the 1,000 contains 0.1, then that small volume that was he pipetted, that 25, will contain how many moles? Okay, so if 1,000 equals 0.1, then 25 will be what? It will be 25 times 0.1 over 1,000, and that gives us 0.0025 moles. So that 25 that was pipetted for the titration actually contains 0.0025 moles of the total moles. Is that all right? Okay.
Yes, sir.
We could have used the formula, but it is advisable that you start with the first principle, and this is the first principle. Okay, so now we know the number of moles in that small portion that we have fetched. And it is those number of moles that reacted with the volume of the acid that was used. Okay, so let's look at our equation of reaction. It is such that 2 moles of sodium hydroxide reacted with 1 mole of the sulfuric acid. And this is where the agreement that I spoke about the last time comes in. We had, where are the ladies? Oh, they are not here. Okay, Charity is here. And Josephine, right? Hello.
Yes, sir.
Joseph's phone
Yes,
is
sir.
off.
Okay, Josephine is not here. Oh, all right.
Yeah.
So we go to the equation and we now look at the agreement. So let's say Charity and Robert. No, Robert looks like my own name. Charity and Evans, they decide in the house that okay, we are going to a program, and this is the agreement they have. Charity says that okay, when we go, anytime I donate 2 Ghana cedis. Evans, you have to give 1 Ghana cedi. So that's the agreement that they have had before going to the program. Now they go to the program. So let's see. Now, half of 2 is 1. So what it means is that any time that, or any amount that Charity will give, Evans will give half of it. If Charity gives 20 Ghana cedis, it means Evans is going to give 10 Ghana cedis. That's the agreement. So Evans gives half of what Charity will give. That's the agreement. Now they actually go into the event and Charity gives 0.0025. This is for 0.0025 Ghana cedis. Then Evans is going to give half of it. Half of. Oh, why is this thing not moving? Evans is going to give half. That is the agreement. When we get this way, it will be easy for us. So we have agreed that whatever you give, I'll give half. So if we've gone there and you are giving 0.0025 Ghana cedis, I only look at half of it, and that's what I'll give. So half of 0.0025 is 0.00125 moles of the A2SO4. Since the reaction is between 25 cubic centimeters of the base and the average volume, that's the titer, and I think our titer was 20. Our titer was 24.5. What it means is that the titer, the volume of the acid used, our average titer, contains this number of moles, 0.00125. That's the moles that reacted. All right. Then we will now reverse it. We are now going back. we equally had large amount of the acid, like 1,000. But out of that 1,000, we didn't use everything. We only used 24.5. So if the 24.5 contains 0.00125 mole, then what will the whole 1,000 contain? So it's like the steps that we used to enter from the side of the sodium hydroxide, we are now going back from the side of the acid. So if 24.5 contains 0.00125, then 1,000 will contain what? We are going to have 1,000 times 0.00125 divided by 24.5, and that gives us 0.05 molar or mole per cubic decimeters. And that is the amount concentration. Like I said, we could have just used formula straight away. C is equal to N over V. So it would have been N, which is 0.00125 over V. V is 24.5. It gives us our answer straight away. So that's the first part. The second part is to find the mass concentration, which we are using the formula amount concentration equals rho over molar mass. So if we make rho the subject, we're going to get rho to be equal to amount concentration times molar mass. We already know how to find molar mass. In this case, hydrogen is 2, oxygen, sulfur is 132, oxygen is 4. 16 times 4, that is 98. So we do that multiplication and we have 4.9 grams per cubic decimeters. And that ends it. If there are questions, you ask. If there are no questions, we'll proceed with the next session. Okay, so now somebody will say that why is it that SHS chemistry practical is all about titration? It's not all about titration. A titration is a technique that we use, and so we can use it to do a lot of things. Okay, so let's proceed with session 2, which is on determination of percentage purity or percentage impurity. You may prepare a solution, but you may have some impurities in it. And in reactions, it is only the pure compound that react. The impurities will not react. And so the yield is not going to be the same as you started with. And so we can find the percentage purity and percentage impurities. In fact, if you pick, let's say, paracetamol, the real paracetamol in it is very small. The rest is just some starch, right? So after this, maybe when you go to the lab, you can pick a mass, you can pick maybe a paracetamol, and then you analyze it, you check how much is the real paracetamol in it. Our objective is to be able to determine the percentage purity or percentage impurity of a substance using titration method. And we start with this formula. Percentage purity equals mass concentration of pure substance over mass concentration of impure substance times 100, or mass of pure substance over mass of impure times 100. So, example, A is a solution containing 20.0 grams of sodium hydroxide per cubic decimeters, and then B is a solution containing 37.6 grams per cubic decimeters of impure sulfuric acid. Probably they just picked or they just fetched a sample that contains, or they fetched 37.60 grams of a sample that contains sulfuric acid and then dissolved it in the 1,000 cubic centimeters, or dissolved it to form 1,000 cubic centimeters of a solution. And so with this, we can clearly tell that it is only the pure sulfuric acid in the solution that will react with the sodium hydroxide. There might be sand in it. The sand will not react with sodium hydroxide. So we can experimentally determine how much that reacted with the sodium hydroxide, and that is going to be the pure sulfuric acid. So we can get the mass of sulfuric acid. We'll divide it by this total mass times 100 to give us the percentage purity. So we are doing this with a question. Put B into the burette, titrate against 25 of A. B is the impure, and then A. All right, so in this case, which one is our titrant? Which one is our analyte? Between A and B. Charity, today you've not spoken. Between A and B, which one is our titrant? Which one is our analyte? Yes, George.
Please, I think B is the titrant.
Okay, you think. All right. Thanks for your contribution. Let me take another response from Evans.
Yes, sir.
Which one is our titrant? Which one is our analyte?
Yes, sir. Since we are putting B in the burette, that one will be our titrant, and then the A will be our analyte.
Okay. Charity, are you there?
Yes, sir.
Which one is our titrant? Which one is our analyte?
Sam.
Okay, you need time to think about it. That's all right. Now let's look at it very well. Technically, we don't know the concentration of the sulfuric acid. Even though we have the mass concentration of both A and B, we don't know the concentration of the sulfuric acid. We know that of sodium hydroxide because in sodium hydroxide, we've been made to understand that the solution contains 20, a man contains other stuff, but in it, we have 24 per cubic decimeter. So we know the concentration of the sodium hydroxide, that is A. All right. So we would say that now you cannot predict, you cannot select titrant and analyte based on which one is put into which equipment. We can only select from concentrations. So it's not about B being put into the burette so it becomes our titrant. We don't know the concentration of B. We know concentration of A. And so A is our titrant. B becomes our analyte. Because that is where we are going to find its concentration. Is that all right?
Yes, sir.
Okay. And so you would realize that when we are starting to find a solution, we will start from A because it is A that we have enough data on. Then through A, we are going to find that of B. Okay, so we are being asked to find the concentration of B in mole per cubic decimeters. So B is our analyte. And we are to do all these things to find the percentage purity of acid in B. We have this table, and so we will proceed to do our average. I hope up to this point it is easy for all of us. All right, so let's now proceed. So we are going to start with A. Okay, and since we have been given the mass concentration, we can change it into amount concentration and start interpreting it. So if 1000 contains 0.6, then the volume that was used, 25, will contain how much? So if 1000 equals 0.6, 25 equals 0.015. Then now we zoom in to look at the agreement between them. What is the agreement? The agreement is that if Charity here gives 2 cedis this time around, George will give 1 cedi. Charity is rich. She's always giving 2 cedis, and the others are giving 1 cedi. Anyway, so George gives half of what Charity gives straight away. So from this, we can just tell that the number of moles of the sulfuric acid in the average titer is half of this, half. And that gives us an answer as 0.0075. Please, do we understand this?
Yes, sir.
Good. So, if this is the moles contained in the average titer, which is just a portion of the 1000 cubic centimeters, it was 22.6. So if 22.6 contains 0.0075, then what about the whole of that 1000 cubic centimeters from which we took the 22.6? It means that one is going to contain 0.33. So this is the concentration of the sulfuric acid. So not the whole of that solution was sulfuric acid. This is the concentration. So what we can do is that now let's go back to the question, look at something. We were given the mass concentration 37.6. So we can find the mass concentration of the sulfuric acid so that we can come and divide by this total and multiply by 100, and we are done. So let's see. Okay, we're here. So we can now convert this one into mass concentration. Okay, and we know the formula. Rho, mass concentration, equals amount concentration times molar mass. This is the amount concentration. We comfortably know it. Molar mass, we can comfortably compute. That is 98 grams per mole. So we do that, we put in our values, it gives us 32.34. So what it means is that out of that 37 that was used in preparing the solution, it is 32.34 that is pure sulfuric acid. So it means that we have a certain percentage of impure substance in there, but we can convert this into percentage by dividing this by the total mass that was used times 100. And so we have it here. So that's 86%. What it means is that in the solution, it is 86% pure sulfuric acid. Then 14% represents the impure substances or other substances that are present. We're able to find that because it is only the reaction that happened was only between sulfuric acid and sodium hydroxide. There may be other components present. If we use a different substance that will react with that component, it will give us the percentage of that very component. Then we can say that all the rest are impure substance. So we have 86%, and that's the end of the session. If there are questions, please ask. If there are no questions, we move on. Okay. So let's move on. With session 3. And in this session, we are going to look now. There's one interesting thing about citation. They almost all follow similar pattern. So once you understand one, it is easy to get the rest, whichever way the question is put. And I hope we are getting something. Okay. So we continue with determination of water of crystallization with our objective as being able to determine the number of molecules of water of crystallization in hydrated salt using titration. Water of crystallization is the amount of water molecules which is attached to an ion or salt in their crystalline state. So we have some equations of reactions between some hydrated salt and some acids. We are going to use this in a question. We have this also. All right. Let's look at how to do that determination. And we are doing that with a question. And the question is as we have there. M is a solution prepared by dissolving 8.2 grams of washing soda crystals in a 250 cubic centimeters volumetric flask and topping it to the mark. What information have we been given here? In this preamble, what information have we been given? Hello? Hello, class?
Hi,
Yes,
sir.
sir.
What have we been given there?
I think we have concentration.
Okay, which one of them?
The mass of M over the volume of 250 cm cube.
So we have mass concentration, right?
Yes, sir.
All right. Then N is a solution of 0.2. So between these two, M and N, which one is our titrant? Which one is our analyte? Yes, George.
Sir, based on what you said, this one M, the sodium carbonate, I think that one is the titrant.
I think you can. What I said doesn't imply this. If you remember it very well.
And like you said, the solution whose concentration is known is the titrant.
Mm-hmm.
And the one we are yet to find is the analyte.
So if you look at it very well, which one are we going to find? Which one do we have enough information on? we have enough information on N. At least in the M, there is a certain X there, which is even unknown.
Okay, sir.
So N becomes our titrant. All right. So we have to find the concentration of M, the value of X, and percentage by mass of water of crystallization. Our average volume of N used as 28.60 cubic centimeters. Okay. So we are going to start our solution from N. If 1000 contains 0.2, then 28.6 will contain how much? It will contain 0.00572. Then we'll go to our equation of reaction, and then we'll look at the agreement. This time round is not charity. It is between Evans and George. Evans 2 cedis, George 1 cedi. Agreement. George gives half of what Evans gives. So Evans has given 0.00572. George is going to give half of it. Half of it, 0.00286 moles of this. But since we only took a portion of this solution, right? It was prepared in thousands, and then we took only 25. So this is contained in that small volume that was used. So that is 25. So if 25 contains this value here, then what will 1000 contain? 1000 is going to contain 0.1144. So that's the concentration. Now, we need to find X. We need to find X. We can find it from molar mass. So what we can do is that we can find the molar mass from here, from the amount concentration. Then we'll equate it to the molar mass of this using the relative atomic masses. X will now be standing alone. We make it the subject and we'll get its value. So we find the mass concentration. That gives us 32.8 grams. And then we try to find the molar mass using the relative atomic masses. So when we do that, then X is going to stand alone. Okay, so we have X standing alone. Now, we can, like I said earlier, we have a concentration here, amount concentration here. We have mass concentration here. So from this, we can find the molar mass. Remember, we said rho, or amount mass concentration is equal to molar mass times amount concentration. So we now find the molar mass from there, and that gives us a value. That is, if we compute this 32.8 divided by 0.114. Now, from the molar mass using the relative atomic mass, we had X standing alone. So we can write molar mass equals molar mass, right? Molar mass equals molar mass. One of the molar masses, we are picking it, or we are taking it from the relative atomic masses. The other molar mass, we are taking it from the calculation, or from the formula that related mass concentration amount concentration and the molar mass itself, such that when we equate the two, X will now be standing alone. So we had the X standing alone, and when we work this out, it gives us 10. So it means that the number of moles or molecules of water of crystallization is 10. Please, do you get this part clearly? Okay. So if it is 10, we can put in place of X as Na2CO3 dot 10 moles of water. All right. We were to find the percentage by mass of water of crystallization. So this side is our water of crystallization. So we are going to put the 10 in place of that, and we are going to divide it, the molar mass here, by the total molar mass times 100. So that will be 18x over 106 plus 18x times 100. We know x to be 10. So we put the 10 in place of x, then times 100, and that gives us 69.2%. 69.2%. And that ends this session also. If you have questions, please ask. If there are no questions, then we move on to the next session. Okay. So in this session, we are looking at relative molecular mass and relative atomic mass of a substance. How do we do that? We hope to be able to determine the molecular mass of a molecule using titration, and then atomic mass of an atom using calculation. And we are doing that with a question. A solution A is a solution of a dibasic acid H2X containing 4.6 grams per cubic centimeters of the acid, whilst B is a solution of 2 grams of NaOH per 500 cubic centimeters. I'm sure at this point you can figure out which one is the titrant, which one is the analyte. And there's a process there for us to go through. What are we finding? Concentration of A in mole per dm cube, which we will always find anyway, whether we are asked or we are not asked, we are still going to find it. The molar mass of H, the dibasic acid, the atomic mass of X, and the percentage of X in H2X. So now we've been given the average volume of A used to be 26.5, but that's not where we are going to start. We are going to start from B. We can change this into amount concentration and start our interpretation from there. So changing it into amount concentration, that is mass over molar mass times volume. That gives us 0.1. So we start with our interpretation. If 1000 equals 0.1, then the small volume that we used, what is it going to contain? All right. This time round, we are trying a different method. We can use the same first principle. If 1000 contains 0.1, then what will the pipette volume 25 contain? Then we'll work it from there. Another way that we can do that, if we don't want to use the first principle, is by looking at the agreement straight away. If we are looking at the agreement, it is between this one and this, and the agreement is 2:1. So N of NaOH over N of the H2X is 2/1. There is 2 here, so 2, and here is 1, so 1. But we know that N equals C times V. So we can now say that C of NaOH times V of NaOH over C of A2X times V of A2X equals 2/1. Now, when we finish with that, we can put in our values. Which one is the C of the NaOH? We can go back to the question. We have the C here. That's if we convert this one into amount concentration, that becomes our C. And that is what we did here. So we have our C here, C of the NaOH here. We have the C of NaOH here. Then V of NaOH is the pipette volume. The pipette volume. Then we come here. The C of A2X is what we are looking for. So that one should stand somewhere. V of H2X is the average titer. This one. So we can now put these values into it, and that gives us 0.1 times 25 over C of A2X times 26. Once again, this is the concentration of the sodium hydroxide. This is the pipette volume. This is what we are looking for. This is the average titer. This is the agreement. 2:1 or 2/1. And when we compute that, it gives us 0.047. If you don't want this, you can go back and you can use the first principle like we have used for the other questions. You're going to get the same thing. All right, so that gives us 0.047 molar or mole per dm cube of the H2X. What are we to do again? So we are to find the molar mass of the H2X, and because we don't know X, we cannot use the relative atomic masses to do that. However, we know the mass concentration, we know the amount concentration. That's what we have calculated, so that we can put those values in here to find the molar mass. That gives us 98. So once we know 98, it means we can find X, because we know hydrogen. Hydrogen is 1. So 1 times 2 plus X equals 98. We make X the subject. So 1 times 2 plus X equals the molar mass. And that gives us 96. Hence, the atomic mass of X is 96. We can check which element has atomic mass of 96. That becomes the element that is supposed to be here. And that solves it. The next is to find the percentage of X in the H2X. We know that we've been able to find X to be 96 So 96 over the total molar mass, which is 98, times 100%, that gives us 97.9. What it means is that for the whole compound, 97.9% of it is X, whilst hydrogen contributes the remaining. All right, so you can use any of those two. This one makes it shorter and very simple. But the first one, the first principle, demonstrates understanding of what you are doing. Friends, any questions so far? Hello?
Hi.
Hi.
Any questions so far?
No, sir.
Okay. We still have some time, and I would want us to proceed to look at the next session. Which has got to do with solubility. Before we proceed, what would you say about solubility? You can share your idea with us, whatever that you know about solubility. Hello? Yes, Robert.
Okay, so the way I understand solubility is how a solid is being soluble in a solvent.
Okay. All right. Okay. We prepare solutions. We dissolve solute in solvents. We can do that until the solution becomes saturated. That is at a point where the solvent is not dissolving the solute again. At that point, the concentration of that solution becomes the solubility. All right, so there is a titration on solubility, and that is what we are looking at in this session. And okay, so our objective is to be able to determine the solubility of a salt using titration. Now, a saturated solution is a solution which cannot dissolve any more solute at a given temperature in the presence of undissolved solute. The maximum quantity of solute in moles or grams that dissolves in a given solvent to form 1 dm cube of saturated solution at a given temperature. That's the solubility. All right. How do we get the maximum quantity of solute? That is when we have dissolved to a point that it is not dissolving again. And so solubility has got a unit mole per dm cube. And if you remember amount concentration, it also has the same unit, which means that solubility indirectly is concentration. But we take the solubility at when we have maximum quantity of solute in the solvent, and that happens at a particular temperature. What do we mean? You may have a temperature of a solution at, let's say, 25 degrees Celsius, and at that point the solvent is not dissolving again. When you decide, and so we have the solubility, when you change the temperature to, let's say, 30 degrees Celsius, then the solution can now dissolve more solute. because you have changed temperature. So solubility, we are looking at saturation at a particular temperature. So that should be the difference. We are starting with a question, and we need to go through the question well. The solution A was made by taking 20 cubic centimeters of a saturated solution of sodium carbonate, and then was now diluted to 1,000 cubic centimeters, whilst B, our titrant, was 0.09 mole per dm cubed. We are going to start our solution from B, but let's try to understand A very well. They said that somebody decided to prepare a saturated solution at a particular temperature. Think the temperature is at 25 degrees Celsius. So at 25 degrees Celsius, there was saturation, or there was a saturated solution. Then the person picked 20, he fetched 20 cubic centimeters out of it, and now prepared a new solution out of this 20. What it means is that, okay, so he fed 20 and then diluted it to 1,000 cubic centimeters. Now, between this 20 and this 1,000, the only thing that has changed is volume, but not the number of moles or the number of particles, because we have only added more volume to this. So if we are able to find the number of moles in the 1,000 is the same as the number of moles in the 20, that cannot be our concentration. All right, so let's proceed. As usual, all the rest are the same. We start with B. We can either use the formula that we have used just in the last session, or we can use the first principle. 1,000, we had a concentration of 0.09 mole per dm cube. So 1,000 equals to 0.09. Then 23.5, the average titer will contain how much? It will contain 0.0012. Then now we look at the agreement. Agreement 2:1. HCl gives 2, sodium carbonate gives half of the 2, 1. So, which means that the number of moles of the sodium carbonate that was pipetted is half of this, and half of it is 0.00106 mole. This is the number of moles in the 25. So we have to convert this. We have to look at the number of moles in the whole of that 1,000. So if 25 contains 0.0016, then the 1,000 will contain 0.042 mole per dm cubed. And this is a point that we have to look at it well. So this is now the number of moles in the 1,000 cubic centimeters of the sodium carbonate. But remember, the volume that was fetched was 20, and that 20 was diluted to 1,000. So if this is the number of moles in 1,000, then this is the same number of moles in the 20, because they fetched 20 and diluted it. So to be able to find the solubility, we can say that 20 cubic centimeters of the saturated solution contains this 0.042, because it was the 20 that was diluted. There was no new addition. 20 was diluted to 1,000, so the same number of moles. So what it means is that the number of moles of the sodium carbonate in the 20 is also 0.42 moles. So our solubility equals N over V. The N is 0.042, and the volume was the 20 that was fetched. And so that gives us 2.1 mole per dm cubed. So that is the solubility at the 25 degrees Celsius. Friends, is it clear? Okay, thank you. All right. So we have our solubility. The next is to now find the mass, and the mass is from the relation C equals mass over molar mass times volume. We can make mass the subject, and if we make mass the subject, we get C times molar mass times volume. Now the C here is the solubility. We can go back and then look at the question. They said that the mass of sodium carbonate that would be obtained by evaporating the 1000 or 1 dm cube of the saturated solution to dryness. All right. So in other words, if we now try and evaporate this 20 to dryness, what are we going to obtain? All right. And that is why we are using this concentration. In other words, the solubility that we had. So C is 2.1, molar mass 106, volume is 1000. And that gives us a mass of 222.6 grams. And that ends the session. There are more examples in the model. You can try your hands on it. You can solve more examples, and that ends the session. If there are questions, please ask. If there are not, we'll proceed to solve our last question, and that's going to end this session. Yes, Evans.
Thank you, sir. Please, the portion where the equation is balanced and you try to make us understand that maybe somebody is using 2 CD, you have to pay half of it.
Mhm.
I want to know whether you are using the coefficient that are in front of the balance equation. If it is so, would you use the reactant or would you use the product?
Okay, thank you. All right, so in a balance equation, if we want to know the ratios, we use the coefficient, the numbers in front. The relation is between the species of interest. Okay, so for example, how can I type something? All right, so let me add an empty slide here and type something here. After that, I'll delete it. I think we still have a little more time. We should be able to do that. So let me write an equation here. Let's say that we have something like HCl plus let's say Na2CO3, giving us, what are we going to get? NaCl plus water, H2O plus CO2. Is it balanced? Yeah, I think it is balanced. Let's put 2 here. Let's put 2 here. Is our equation balanced? Yes, it is balanced. Okay. Good. What is our mole ratio here? This is the ratio for all of them. We have 2 for HCl, 1 for sodium carbonate, 2 for NaCl, 1 for water, 1 for carbon dioxide. This is the agreement, the general agreement for all of them. So this is just like 5 people agreeing on their contributions when they go to an event. Let me see if we are up to 5. Okay, so Robert Chumesi says, when we go, I'll give 2 Ghana cedis. Charity says, I'll give 1 cedi. Code e-learning says, I'll give 2 cedis. Evans says, I'll give 1 cedi. George says, I'll give 1 cedi. That is the agreement that we've all had. Now, as for which 2 of them to relate, depends on what you are looking for. Let's say that I have enough information on HCl and I'm looking for, let's say I have enough information on HCl and I want to find something here. I want to find maybe mass of water or something on water. Then I'm going to relate HCl and water because it is water that is the species of interest to me, whether it's at the product side or reactant side. That is what I'm finding information on. So in this case, I will now relate HCl and water. If it is sodium chloride that I want information on, then it means I'm going to relate, or I'm going to look at the agreement between HCl and NaCl, which is 2:2. They all give equal amount. If it is between, or if it is Na2CO3 that I want, then my relation is now between HCl and this. So that's how it is. What you are going to relate it to depends on which species of interest, which species you want information on. Is that all right? Okay. Thank you. So I'll take that slide off. Oh, all right. I hope I've not deleted anything. Okay, so determination of amount of ions and actual number of ions in a solution. Objectives are to determine the amount of ions in solution, determine the actual number of ions in solution. And we start that with a question or a problem. So A, our titrants, B, our analytes. There's an exercise for us to do. What are we to find? Concentration of potassium hydroxide in mole per dm cube, in gram per dm cube, amount of potassium ions, hydroxide ions, number of K and OH. They are there plenty, but very simple to deal with. So let's go and start from the HCl. 1000 contains 0.1. What will 22.5 contain? So 22.5 will contain 0.0025 moles. We look at the agreement between them. The agreement is such that Evan gives 1 cedi, Robert gives 1 cedi from this balanced equation. So always make sure that the equation is balanced. If the equation is not balanced, you cannot do the mole ratio. This is a balanced equation. It is 1:1. What it means is that if This one gives 1 CD. This one will also give 1 CD. So that's HCl gives 0.00225 moles. It means the moles of KOH will also be that, the same thing. All right. Then when we are done with that, that is the moles in the volume of the pipette. So we need to take it back to 1000. So if 25 contains 0.00225, then 1000 will contain 0.09. If that is 25 equals 0.00225, 1000 equal to X. You make X the subject, it gives you 0.09 moles of the potassium hydroxide. So this is the amount concentration. We can find the mass concentration. We know the molar mass of potassium hydroxide 56. So mass concentration rho is C times molar mass. C is what we have found here. The molar mass is what we've computed for here. So we put in the values and it gives us 5.04 grams per dm cubed. So we are done with the first aspect. Then I will go to the ions. This KOH will dissociate to give us K plus and then OH minus, right? And we can still do our mole ratio there. So moles of KOH that reacted with HCl is 0.00225 at the end point. We split this into ions and it gives us 1 mole of potassium ions, 1 mole of hydroxide ions. So here also the agreement is 1:1:1. So it means that 1 mole of potassium hydroxide gives or produces 1 mole of potassium ions, 1 mole of hydroxide ions. So the moles of potassium ions will also be 0.00225. The moles of this hydroxide ions will also give us 0.00225. So the next is to now find the number of ions. And with this, we'll need this mole with the Avogadro's number. That will give us the actual number of ions. And because the moles are the same, we expect equal number of ions for each of them. So K plus is 1.355 times 10 to the power 21 ions, the same as the hydroxide. And that ends this session also. Friends, are there any questions?
No, sir.
All right. If there are not, then what it means is that, okay, George.
Thank you, sir. Please, I just want you to help me to write the subscript and the superscript when you are using a laptop. If let's say you are writing an equation,
It's control plus for subscript.
control
plus
plus
for subscript.
Okay.
And then I'm coming.
Okay, sir.
Let me put something here. Then control shift plus for superscript.
Control shift plus
for superscript.
Okay, sir. Thank you, sir.
All right, you're welcome. Okay, so we are ending it here, and that will mean that our next meeting will be after. Is it a break or yeah? But I think it will be after some time. Do we have a new hand up? Okay, George. Oh,
it was an old hand.
Okay. All right. Yes, Evans.
Yes, sir. So after this one, the break is quiz. After the break is quiz. So after the quiz is presentation.
Now there is one more face-to-face. unit 4 before the face-to-face. Before the presentation. So
Yes, sir.
yeah. Okay, so I wish you all the best in the quiz that you are going to write. I'm sure that it's going to.
Please, we are trying to
Uh-huh.
access questions from the e-learning platform, but there are no questions there.